Okay, recall. If f of x comma y comma z is a scalar field or a scalar function, so a function with multiple inputs, we'll go with x, y, and z as the three input variables. Let's go with an example even. How about like xy plus 2xz plus y times z cubed? Then the gradient of f is going to be a vector field. More specifically, it's the partial derivative with respect to x of f, comma the partial derivative with respect to y of f, comma the partial derivative of z with respect to f. I know you're used to maybe seeing that f there, and you're perhaps used to a little bit more the notation of f sub x instead of the partial derivative, instead of the partial derivative of f with respect to x, but you can kick that f off to the side and have notation that looks like this, which is going to be helpful in a moment. We'll compute for this example that we're going to get y plus 2z, comma the partial derivative with respect to y will be x plus z cubed, and the partial derivative with respect to z will be 2x plus 3yz squared. Okay, we're going to define the gradient symbol alone without an f. This sounds a little funny. We'll just define this to be, just looking above, partial derivative with respect to x, comma partial derivative, let's write that better, comma partial derivative with respect to y, comma partial derivative with respect to z. So it's like, just imagine taking the f's out that were circled right there is all. So you can think of this like, so this is a thing to memorize right here, but it won't be so bad probably to memorize. You could think of it like, even if it's not really this, you can think of gradient of f like either, f is scalar multiplying, against this symbol. For that matter, instead of thinking of f as the scalar and this, well, yeah, that's probably the better order. This as the scalar times this as the vector, instead of this as the scalar times this as a vector. Okay, so when you see this symbol alone, we're thinking of creating a vector that looks like this. I know this looks a little funny, but it's going to be helpful to keep track of the various things that we're going to be defining in just a moment. So, given a vector field, so we'll call that vector field capital F. We'll leave out for now the x comma y comma z. We'll just leave that out. Okay, that will be assumed or understood. Equals angle bracket capital P comma capital Q capital R. Same deal. We'll leave out the of x comma y comma z. So as an example here of a vector field, we might have capital F is equal to angle bracket 2x plus yz comma xy squared plus z cubed, comma x to the fourth times y times z, close angle bracket. So in our example here, there's capital P, there's capital Q, there's capital R. Then we're going to define a new thing called curl of f. So curl of capital F arrow. So take a vector field, we're going to define a new thing. This can also notation-wise be written, the symbol that we just looked at up here, okay, the gradient symbol, cross product f vector. I would suggest that you take this, of course that is just notation, but you memorize it this way. So this may look a little funny, it takes a little getting used to, but you'll be fine, is that when you take a cross product, you have I, J, K, and then think about it, take the things that are part of this, treat it like a vector, like this thing that seems to look like a vector right here. So we'll have here partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And then in the next row, in these next spots, we need the components of f, which we've just generically called capital P, capital Q, capital R. So P, whoops, capital P, capital Q, capital R. Go there. If we go ahead, so I hope by memorizing this, you can come up with that. So, sort of memorizing this directly is I would say unnecessary. And then let's write out what this should be. Just do what a cross product normally does, and we'll have, I times, and then the 2 by 2 determinant this block, right? So we've got this times this, yeah, but instead of saying times, what we'll really say is that we're going to have the partial derivative of r with respect to y, and then we've got this times that, but again, not times, and we'll go with this derivative notation before that, saying the q. So partial derivative of q with respect to z. Then we have a minus j times, and then so now we're looking at those entries, right? If we hide the middle column, so we've got partial derivative of r with respect to x first, partial derivative of r with respect to x, minus partial derivative of z with respect to p. Partial derivative of p with respect to z. I didn't say that right. Partial derivative of p with respect to z, plus vector k times, and then we've got this 2 by 2 determinant block over here. Partial derivative of q with respect to x. So dq over dx minus partial derivative of p with respect to y. dp over dy. Okay, so this is a way that books often define it, so hold on to that. But trying to memorize this directly is really difficult, challenging. There's minus signs, and we probably should distribute this minus sign in and so on. But I think just thinking of this will make it a lot easier to keep track of all of what's going on. So let's do the following. Let's practice this. It's not bad. So if you have a vector field, namely the vector field we had up here, so angle bracket 2x plus yz, comma xy squared plus z cubed, comma x to the 4th yz. To practice, let's find the curl of f. So, the curl of f, which easiest to memorize by writing that, okay, is, now if we implement this, we'll have I, j, k, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and I should have left a little bit more space here. Let me space things out. And then the components of f, so 2x plus yz, and then xy squared plus z cubed, and x to the 4th yz. And if we take this 3 by 3 determinant, we'll have I times, and we'll do a partial derivative. Sorry, this is probably going to get too messy to circle all the things, but take a look here and take a 2 by 2 determinant. But what we mean is partial derivative with respect to y of this minus partial derivative with respect to z of that. Right? So let's go ahead and just compute those things. We'll have here x to the 4th z minus let's see, when differentiating with respect to z here, the first term is going to be gone. We're just going to be left with just the 3z squared, yeah? 3z squared there. Okay, then we'll have minus j times, and we've got here this. Okay, so partial derivative of x to the fourth yz with respect to x will be 4x cubed yz minus partial derivative with respect to z of 2x plus yz. Okay, so we'll be left with y when we do that. And then plus k times, and then look at this 2 by 2 determinant. So first partial derivative with respect to x of x y squared plus z cubed, and that should land us with just a y squared, minus, and then partial derivative with respect to y of 2x plus yz, and that should give us just give us z. We're technically done with the work, but let's just organize things better, distribute the minus sign that we see here, and I would just prefer perhaps to write actually in angle bracket notation. X to the fourth z minus 3z squared is the first component, comma. If we distribute the minus sign, we could just think of it as swapping the order of terms here. So how about y minus 4x cubed yz, comma, y squared minus z as the third component. Okay, so what happened here? We're done with the problem, but let's just summarize what we did here. We took the curl of the vector field, angle bracket 2x plus yz, comma, xy squared plus z cubed, comma, x to the fourth yz, and obtained. We actually got a new vector field right over here. Yeah, the output is in the shape of it's a vector with input variables x, y, and z. So we obtained the vector field. Angle bracket x to the fourth z minus 3z squared, comma, y minus 4x cubed yz, comma, y squared minus z. The point being, this would happen in general, right? It wouldn't be special just for this one. So just the one key thing to note here is that the curl of a vector field is a vector field. So let's take just a moment to talk through what curl really represents. This is perhaps a challenging idea. Try not to stress yourself out over this too much, but if you're just curious, what is curl? What's a physical interpretation of curl? Physical interpretation of curl. The short story is you can imagine that your original vector field, like perhaps this one here, represents, your vector field over here represents maybe how water is swirling around. So at the point x comma y comma z, you plug in the value of x, y, and z, and then you get a vector, and the vector that you get has direction and magnitude and tells you that at that xyz location, how is the water pushing things? What's the current? What's the direction of the current, and how forceful is the current? How strong is the current? And then what curl, in a sense, is computing for you is at a certain xyz. When you plug in your xyz into this, it's telling you how much the water swirls, how much it curls, how much it rotates, and in what direction, in a sense, the rotation of the water is happening in. So let's take a look at somebody else's app to see a picture of what's going on. Okay, so just quick credit is that this is not my app. I do not know how to make an app that does this, I would really be interested in making this. But mathinsight.org/curl_subtleties. And I scrolled down towards near the bottom of the page. There's a section that says curl that is the opposite of macroscopic circulation. So they define a vector field here. They're probably, well, not probably, they're using the notation of a different book where you see in the denominator a scalar, that's fine, but in the numerator, I would be using angle bracket symbols right there and there. But anyway, there's a vector field. Here is their computation of the curl. Again, in the numerator, this 0, 0, -1, I would be having in angle brackets. And so you see over here a picture of this vector field. And you'll notice that the basic idea behind it is that the further on out you are from the origin, but only in the xy plane. So let's say it this way. Yeah, dare I say it this way? How about in cylindrical coordinates, when the r value is big, then you have a big number in the denominator. So actually, if we look at this from where positive z is, you can kind of see the effect of this with tiny, tiny, tiny arrows out here because the magnitude is small. And the closer you move in towards z, and the height not mattering here, you'll notice here that there's no z variable at all in how the vector field here was defined. So it should look the same on all levels, actually. Yeah, you can kind of see that effect here. And the curl, although it's been computed here, you don't really need to look at this picture over here. This is just a flattened view from the top. But over here, the idea is you imagine a beach ball and allow the beach ball to spin however it wants to, but it has to remain in place. Like the center of the beach ball needs to be wherever it is. And then how would the beach ball spin? Like based on where the ball is currently located, it would, I guess, spin in this direction. And for this direction, there's say at one of the poles you have an arrow, and that arrow ends up being the value of the curl. So as you move this thingy to be closer to not quite the origin is maybe what I should say, because it won't matter as long as the r value in cylindrical coordinates gets tiny, then you're dividing by a small number, even right here in the curl formula. In the computation of curl in this example, and so the ball spins more. So how much the ball is spinning by is actually captured by the magnitude of the vector that you see in green down here. Okay, so in the curl of a vector field is a vector field, and the vector that you get, its normal vector in a sense of the direction of the swirl tells you which direction the swirling is occurring in, and then the length of that vector tells you how fervently that rotation occurs.